It's this thing called a load case manager. Now, load cases are really just studies when it comes down to it. When we're taking a look within the SolidWorks interface, studies can be a fairly unwieldy thing to be able to organize. You end up with a lot of tabs along the bottom, and within those tabs you really don't have a whole lot of feedback as to what the settings are in each of those scenarios. So I want to show you this tool we've created called the Load Case Manager. When we go ahead and actually look at the manager, essentially what it is a tabular format for being able to set up different scenarios, and then those scenarios can have different settings for each of the inputs. So when you're looking at things like your fixtures and loads, we've got 3 boundary conditions from fixtures, and then down here we've got 4 different loads, different directions, gravity, and torque. And what those settings are for each study is not always the most easy thing to look at. And how you can switch them for different scenarios is also a difficult thing because we're changing those settings per tab. Well, here in this Load Case Manager, we can simply go ahead and create different load cases. And in those, we can choose to suppress or activate different restraints, as well as the loads, whether they're suppressed or whether they're on, and then what the value of that load happens to be for that particular load case. It's as easy as clicking here to add a new one. We'll call it whatever we want. And now I can go ahead and turn on whatever in this case restraint or force I want to put on, which is going to be the torque force. You can also go ahead and create these load case combinations. Now what a load case combination amounts to is different scenarios combined with each other in a different way. So if I wanted to do a scenario here, for example, where maybe I wanted to go ahead and take this 20G vertical load and I wanted to multiply that by whatever, 2 times something. Well, 2 times the lateral movement would be great. So that would be just a different way to set up a combined or a more powered type of study here. Now, just in the interest of time, I'm going to switch over to a tab that I've got where these load cases are run, and then we're going to go to the Results tab. Another tabular format, what this is going to do is lay it out in such a way that we can see what the results are side by side as well. So, for example, if I'm looking up here in my graphics area and I want to take a look at, we'll just take a look at stress. Stress is going to give me this colorized plot. But when we want to look at the different load cases, we simply select downward, which means downward had 2,000 newtons turned on, and then here is going to be our resulting displacement and stress. Lateral was not using that downward force. It was actually using the right load. But as you take a look at the part changes for each one of these scenarios. We're seeing the plot as if we're activating the plot for that tab. Again, only in this case, it happens to be more side-by-side, comparable, as well as a one-stop shopping interface to make these quick changes. I'm going to switch over next to this dynamic plot that we've got in this tab. When we're doing dynamics, there's a lot of inputs. Really, it's more irregular in many cases, whether it's a harmonic or done by a plot or a text file that's giving different forces. When we're dealing with any type of dynamic responses, the input is going to be our load case, but then our output, our results, are going to be how we read that. And all along with dynamic simulations, we've been looking at these things called frequency response graphs. Now, this frequency response graph tells me very little, tells me some, but very little. It tells me that the magnitude, the highest part that we had here, happened to be around 436 hertz with our frequency. But other than that, the rest of this data is really kind of unusable. So what we've created is a new results plot, and it's called a frequency response graph. What this gives you is the capability to use the effective mass participation and show these things in more of a bar graph type of a way instead. And then here it's really easy to see where the Z component, the Y component, and the X component really contribute these different mode shapes. First mode shape, obviously, Z is the maximum contributor, where in the second mode shape, Z doesn't come into place at all. But it does show up in other areas and a little bit lower loads in this particular case, the mass participation. We also have a plot similar to this, but a little bit higher order, that's called the cumulative effective mass participation. And what that's going to do is show this in a different type of a chart, but it gives you the same detail that we can glean. So here early on in our mode shapes at the frequencies, we're getting very low X and Y values, but Z is very high. And then as they start to converge at different modes, we can see that Z moves more to the middle where X and Y are going to bracket that a little bit more. But in any event, it's much more usable data to glean off of this than we had in previous types of charts.